On July 24, 1945, a single weapon turned a heavy engineering problem into a structural crisis. The Imperial Japanese Navy aircraft carrier Amagi was moored in the protected anchorage of Kure Harbor when she was struck by a bomb weighing 2,000 pounds. This was not a glancing blow. The weapon struck amidships between the two aircraft elevators and penetrated roughly 25 feet of deck structure and internal voids before detonating on the upper hangar deck. The physics of this explosion did not merely breach the watertight envelope. The overpressure event blew out the hangar walls and buckled the flight deck for over 200 feet. That specific structural failure dictated the salvage plan. The shattered hangar sides and flight deck could not be made watertight, so they had to be removed before righting could even be attempted. The ship did not sink immediately, but the integrity of her upper hull was shattered. The Amagi was an Unruh-class carrier designed for a war that had already shifted against her. By the summer of 1945, she was effectively a floating anti-aircraft battery moored 50 meters off the shore of Mitsukojima. She sat in shallow water, camouflaged against the air raids that were systematically dismantling the Imperial fleet. The damage from July 24th was severe, but the carrier remained upright. The engineers attempted to control the damage, but the vessel was a static target. 4 days later, on July 28th, the ship was hammered again, by additional hits, and by close port-side near misses, whose underwater shock and fragments opened plating and accelerated flooding. American aircraft placed heavy ordnance in the water close to the port side of the carrier. Water does not compress. When a high explosive detonates underwater, the shockwave travels as a hammer blow against the hull plating. These near misses ruptured the underwater shell of the Amagi along her port side. This converted the damage scenario from structural trauma to a fluid dynamics crisis. The ocean began to enter the lower compartments. This introduced the mechanism of progressive flooding. Progressive flooding is the creeping failure of internal security. A ship is designed with watertight bulkheads to contain damage to a single zone. When those boundaries are compromised by shock damage or open hatches, water travels from the breached compartment into intact spaces. It finds cable runs, ventilation ducts, and warped door frames. As the water moves, it adds weight where the designers never intended it to be. On the Amagi, this weight accumulated on the port side. The pumps were overwhelmed, and the counter-flooding measures failed to arrest the list. By the morning of July 29, 1945, the physics of buoyancy had lost the war against gravity. At 10 in the morning, the carrier began her final rotation. She rolled slowly to port. The shallow depth of the harbor meant she could not sink completely. Instead, she capsized until she hit the seabed. The ship came to rest at a list of 70 degrees. The starboard side remained above the surface, exposing the bilge keel and the massive bronze screws to the air. The port side was buried deep in the harbor mud. In the silence that followed the air raids, the Amagi was no longer a warship. She was a tangled mixture of steel and sediment. Yet she was not entirely abandoned. In a detail that underscores the rigid discipline of the era, a small team remained with the wreck. A fringe detail from the historical record notes that 1 officer and 4 petty officers were assigned as a caretaker crew. They lived on or near the capsized hull, maintaining a symbolic watch over a vessel that was physically wrecked. They were guarding a corpse. The salvage engineers who arrived later faced a geometry problem that seemed impossible. The ship was lying on her side in the mud. The upper structure was a ruined birdcage of twisted steel caused by the 2,000-pound bomb. The hull was full of water and the port rail was acted upon by the immense suction of the seabed. To clear the harbor, they would have to right a ship that was structurally broken. The question facing the survey team was not just how to lift the hull, but whether the hull was strong enough to survive the forces required to move it. 70 degrees is a terminal angle for a heavy displacement hull. When the Amagi settled into the mud of Kure Harbor, she did not stop at a recoverable list. She rolled until she was nearly horizontal. This specific angle of 70 degrees transformed the vessel from a ship into a steel barrier. The port side flight deck rail was driven deep into the sediment while the starboard bilge keel pointed at the sky. This geometry dictated that no standard damage control procedure could ever right her. To understand why she ended up in this extreme position, we must look at the mechanic known as the free surface effect. The free surface effect is the specific instability caused by unconfined liquid moving inside a vessel. A ship is stable because its center of gravity is low and its center of buoyancy is high. When a compartment is flooded entirely, the water adds static weight, which sinks the ship deeper but does not necessarily capsize it. However, when a compartment is only partially filled, the water is free to slosh across the deck as the ship rolls. On July 28th, the Amagi took on water from the port side ruptures. At the same time, crews were pumping tons of water into the hangar to fight fires. This water was not contained in small tanks. It was spread across the large open decks. As the ship leaned slightly to port, all that water rushed to the low side, instantly shifting the center of gravity in that direction. This created a feedback loop. The more she listed, the more the water shifted, and the more the stability vanished. This sloshing weight acts like a pendulum that refuses to swing back. It effectively erased the ship's ability to right herself. The resting position of the carrier introduced a second complication regarding the terrain. The seabed at Kure was not a flat concrete slab. It was a sloping bank of soft mud. The Amagi did not settle evenly. This leads us to a specific anomaly recorded in the survey data. The wreck developed a condition known as the high stern. The harbor floor deepened as it moved away from the shore of Mitsukojima. Because the Amagi was over 700 feet long, her bow sat in deeper water than her stern. While the bow was completely submerged, the stern flight deck remained largely above the water level. This meant the ship was not just rolled over, she was twisted. The bow was supported by water and mud, while the stern was hanging largely unsupported in the air. This placed immense torsional stress on the keel. The ship was being wrung out like a wet towel. This uneven support created a critical risk for any future salvage attempt. If the engineers tried to pump water out of the stern section first, the loss of buoyancy might cause the stern to snap off under its own weight. Conversely, the bow was buried so deep that the mud was acting as a seal over the damage. The port side hull was inaccessible. The list of 70 degrees also meant that the internal layout of the ship was now vertical. Walls became floors and floors became walls. Walking through the interior was impossible. Any survey team entering the wreck would be climbing up the bulkheads using door frames as ladders. The oil and debris that would normally float on the surface of the water inside the hull were now coating the port side walls, which were currently the floor. The final constraint was the tide. The shallow water meant that the environment around the wreck was dynamic. At high tide, the water lapped against the island superstructure. At low tide, the starboard screws and the red underbelly of the hull were exposed to the air. This confirmed that the ship was resting in the intertidal zone where oxygen and saltwater mix most aggressively accelerating corrosion. The salvage team was not just fighting gravity, they were fighting a structure that was slowly dissolving and twisting under the stress of its own geometry. The aerial reconnaissance photographs from July 1945 presented a visual lie. They showed a small extension of the island coastline covered in dense foliage, civilian roads, and wooden buildings. But the magnetic anomaly detectors and the target profiles indicated a massive steel displacement. This contradiction was the result of one of the most elaborate static defense projects of the war. The Amagi was hiding in plain sight. To protect the carrier while she was moored 50 meters off Mitsukojima, the crew had constructed a fake town directly on top of the flight deck. This was not a simple paint scheme. It was a three-dimensional architectural disguise. They planted real pine trees and brush to break up the hard, straight lines of the steel deck. They erected plywood houses and laid out canvas strips painted to look like dirt roads. The objective was to blend the 700-foot warship into the topography of the adjacent island. It was a desperate piece of combat engineering. It failed to stop the bombers, but it succeeded in complicating the survey. When the salvage teams from Hitachi Zosen arrived in 1946, they faced a wreck that was a tangled hybrid of industrial steel and rotting lumber. The camouflage netting had snagged on the twisted metal of the bomb damage. The fake buildings had collapsed into the real wreckage of the bridge. Before the engineers could even assess the hull, they had to clear away the debris of this failed disguise. The salvage authorization came in 1946 with a clear mandate. The Amagi was blocking a berth that was needed for the reconstruction of Japanese maritime transport. The goal was clearance. To achieve this, the engineers had to map the underwater damage. This required divers to descend into the harbor mud. The survey conditions were hostile. The water in Kure Harbor was opaque with silt and oil leaking from the submerged machinery. The divers could not see the damage. They had to feel for it. They walked along the port side hull, which was now the bottom of the wreck. They used their hands to find the jagged metal lips of ruptures and fragment holes caused by bombs and close underwater near-miss detonations. They measured the length and width of every hole using physical rules and lead lines. This data was sent to the surface to answer one binary question. Could the hull be sealed? This brings us to the engineering concept of the watertight boundary. A watertight boundary is not just a wall that stops water, it is the absolute line that defines the buoyant volume of the ship. In salvage engineering, you cannot lift a vessel unless you can define exactly where the ocean stops and the ship begins. If that boundary has a single gap, the size of a coin, the pumps will eventually lose the race against the sea. On a capsized ship, this boundary is difficult to establish because the pressure changes with depth. The divers confirmed that the lower hull was viable. The steel plating on the port side could be patched. Underwater welders could attach steel covers over the bomb holes to restore the boundary. The pumps could then drain the lower compartments and restore buoyancy to the bottom of the ship. This was the good news. The bad news was the upper structure. The survey confirmed that the 2,000-pound bomb from July 24th had done more than just bend metal. It had destroyed the structural continuity of the hangar deck. The flight deck was blown outwards. The elevator shafts were warped. There was no way to establish a watertight boundary on the top third of the ship. The volume of the hangar was enormous, but it was compromised beyond repair. This created a massive physics problem. If they tried to right the ship in its current condition, the upper structure would act as a giant scoop. It would flood instantly as the ship rolled. Even worse, the weight of that damaged steel was acting as a heavy lever arm, keeping the ship pinned to the mud. The survey team realized that the ship was too heavy to save. To lift the Amagi, they would first have to destroy a significant part of her. The engineering team faced a binary decision that defined the entire operation. They could attempt to rebuild the shattered upper hangar deck to make it watertight, or they could accept that the structure was a total loss. The survey data from Chapter 3 dictated the answer. The 2,000-pound bomb had compromised the hangar walls so severely that patching them would require building a new ship inside the wreck. The solution was subtraction. If the upper structure could not be sealed, it had to be removed. This decision was driven by the concept of dead weight. In naval architecture, dead weight describes mass that contributes to the downward force of gravity but offers no potential for buoyancy. On an intact ship, the hangar deck is a buoyant volume because it is enclosed by watertight steel. On the Amagi, the hangar was a sieve. If the salvers tried to right the ship, the submerged hangar would fill with water immediately. The steel structure would act as an anchor, dragging the center of gravity away from the keel. To restore stability, the engineers had to amputate the top third of the aircraft carrier. The scale of this demolition was immense. They needed to remove over 200 feet of buckled flight deck and the heavy steel ribs that supported it. In a standard shipyard environment, this would be done with oxyacetylene torches and cranes. But the Amagi was lying on her side in a tidal zone. Sending men with torches into the twisted, semi-submerged wreckage was slow and dangerous. The gas lines would snag on debris and the tidal currents limited the work window. To bypass these constraints, the salvage team adopted a fringe technique rarely seen in standard recovery manuals. They used dynamite. Instead of surgically cutting every beam, they treated the carrier like a demolition site. They placed linear charges along the structural frames of the flight deck and the hangar walls. This was not a chaotic bombardment, it was a precise sequence of cutting charges designed to sever the steel connections instantly. This method converted days of cutting time into milliseconds of fracture. The blasting weakened the structure enough that cranes could pull massive sections of the flight deck free from the hull. They stripped the ship down to the hangar floor. The elevators, the gun tubs, and the island superstructure were cut away. The goal was to reduce the profile of the ship until it resembled a long, shallow barge or canoe. Removing this mass solved two problems at once. First, it eliminated the dead weight that was pulling the ship over. Second, it lowered the center of gravity. By removing the high steel, the weight of the engines and the double-bottom hull became the dominant force. This naturally encouraged the ship to want to return to an upright position. While the explosives were doing the heavy work above the waterline, a different team was working below it. Divers descended to the port side to seal the ruptures caused by the near misses. This was the counterpart to the Demolition. While the top team was removing weight, the bottom team was restoring buoyancy. They welded patches over the 500-pound bomb holes and the seam ruptures. They installed cofferdams around the intakes. They were re-establishing the watertight boundary on the lower hull. By the summer of 1947, the Amagi was no longer a recognizable aircraft carrier. She was a sealed steel trough lying on her side. The physics had been altered in her favor. The top was light and the bottom was buoyant. Theoretically, she was ready to roll back to an even keel. But there was one final force holding her down. The port side of the hull was not just resting on the seabed, it was embedded in it. The mud of Kure Harbor had formed a seal around the bilge keel, creating a vacuum effect that no amount of weight shedding could break on its own. Buoyancy is a vertical force that pushes a submerged object toward the surface. However, in the salvage of the Amagi, the engineers were fighting a force that acted in the opposite direction. This was the phenomenon of mud suction. When a flat steel surface, like the port side hull of an aircraft carrier, is pressed into soft sediment for 2 years, the water between the steel and the mud is squeezed out. This creates a vacuum seal. The pressure of the ocean above holds the ship down against the seabed. This invisible bond can require thousands of tons of extra force to break. This was the breakout force that the survey team had to overcome. To generate the necessary power, the salvage team could not rely on internal buoyancy alone. Even with the flight deck removed and the lower compartment sealed, the hull did not have enough leverage to peel itself out of the mud. They needed an external mechanical advantage. To achieve this, they utilized large steel salvage pontoons. These pontoons were essentially airtight steel tanks. The engineers used a system of flotation tanks and pontoons arranged across the hull, some kept buoyant, others deliberately flooded, to generate the righting moment needed to lever the ship upright. They flooded these pontoons to sink them into position and then secured them with heavy chains wrapped around the hull structure. Once secured, they used compressed air to blow the water out of the pontoons. This converted the tanks into massive balloons of air attached to the side of the ship. This application of force relies on the engineering principle of righting moment. Stability is not just about weight, it is about rotation. Righting moment is the measure of the force required to rotate a ship back to an even keel. It is calculated by multiplying the buoyant force by the distance from the center of gravity. By attaching the pontoons to the high side of the list, the engineers created a long lever arm. The pontoons pulled upward on the starboard rail while the weight of the engines pulled downward on the keel. This combination created a rotational torque designed to twist the ship free from the suction of the harbor floor. The final operation began in late July 1947. The team activated the pumps to drain the sealed compartments in the lower hull. Simultaneously, the air compressors filled the pontoons. The hull groaned as the forces equalized. The steel patches held. The internal water level dropped, transferring the weight of the ocean back to the structure of the ship. On July 31, 1947, the physics finally aligned. The buoyancy generated by the empty compartments and the external pontoons exceeded the grip of the mud suction. The vacuum seal on the port side broke. The Amagi rolled away from the seabed. She did not shoot to the surface like a cork. She rotated slowly and deliberately until she settled on an even keel. The result was a vindication of the destructive strategy used in the previous phase. The ship that surfaced was not the towering warship that had capsized in 1945. She was a low, flat hull with jagged steel stumps where the hangar had been. She looked more like a barge than a carrier, but crucially, she was floating. The draft was stable, the list was corrected. The resurrection of the hull proved that the decision to use dynamite was correct. If the engineers had attempted to lift the ship with the flight deck intact, the center of gravity would have remained too high. The righting moment would have been insufficient to overcome the mud suction, and the ship likely would have rolled back over or snapped her keel. Instead, the Amagi was now a floating unit of scrap steel ready for the final stage of the process. The path to success was open. The final phase of the Amagi salvage operation was defined by a ruthless efficiency. While the ship had spent over 700 days resting on the bottom of Kure Harbor, Her life as a refloated vessel lasted fewer than 140 days. The deadline for the operation was strict. The post-war administration required the berth to be cleared and the steel to be returned to the furnace. There was no sentimentality attached to the hull. It was treated strictly as a resource stockpile. On August 30th, 1947, the tugs took the Amagi under tow. The journey was short. The wreck was moved from the shallows off Mitsukojima to the dry dock facilities at the Hitachi Zosen yard in Kure. The vessel that arrived at the breaking yard bore little resemblance to the warship that had launched in 1944. She was a pontoon-stabilized raft of corroded steel. The flight deck was gone, the guns were gone, the engines were salt-ruined dead weight deep inside the hull. The scrapping process began immediately. The dismantling of a ship is effectively construction in reverse. The gangs of cutters started at the highest point and worked their way down to the keel. The steel plating was cut into manageable sections and lifted away by cranes. The copper wiring was stripped. The heavy machinery was broken down. By December 12, 1947, the job was complete. The Amagi had been erased from the harbor charts. This rapid disappearance stands in contrast to the visual landmark the wreck had become during her 2 years in the mud. This brings us to a specific detail regarding the starboard propellers. For the duration of the capsizing, the Amagi had rested at such a severe angle that her starboard screws were often exposed above the surface. In a harbor cluttered with debris, these bronze blades had served as a static reference point for local traffic. At low tide, they were high and dry, a towering reminder of the scale of the submerged obstruction. At high tide, they were awash. For 2 years, they functioned as a massive, impromptu tide gauge for the harbor pilots. When the ship was righted on July 31st, that landmark vanished back underwater. When the ship was scrapped, those screws were likely among the first components recycled due to the high value of their bronze alloy. The legacy of the Amagi is not found in naval combat records. She never launched an airstrike against an enemy fleet. Her only engagement was the passive absorption of ordnance while moored to an island. Instead, her significance lies in the engineering data generated by her recovery. The Salvage proved that a capital ship compromised by massive structural damage and extreme geometry could be recovered through the aggressive application of weight shedding. The decision to use dynamite to remove the upper structure was a departure from standard preservationist salvage. It accepted that the ship was already dead. The engineers did not try to save the carrier, they only tried to save the buoyancy. By converting the complex problem of a capsized warship into the simpler problem of a sealed barge, they turned a total loss into a successful clearance operation. The steel from the Amagi did not go back to war. It was melted down and fed into the reconstruction of Japanese infrastructure. The railway tracks, the girders, and the sheet metal produced from her hull helped rebuild the cities that had been targeted by the same bombers that sank her. In the end, the operation was a complete success. The hazard was removed, the harbor was cleared, and the books were closed on the Unruh class.